Next, we will discuss about active elements. Active elements. Active elements. I already told that all type of battery source, batteries, generators, op-amps, all these are active elements. Now here we will discuss about the source, voltage source or current source. Now source may be two types. Maybe sources are two types. One is voltage source, another is current source. Now this voltage source may be ideal voltage source or real or practical voltage source. This is hold same for the current source also. That means current source also ideal one, ideal voltage source, current source or practical current source. Let's start from ideal voltage source. Ideal voltage source. What is an ideal voltage source? We have said earlier that the all the elements, maybe voltage source is an element, so actually it has two terminals. So voltage source basically a two terminal device. Ideal voltage source is a two terminal device which maintain a constant voltage or which is a particular value of voltage at its terminal regardless of any value of current flowing through that terminal. That means is the voltage remains constant whatever value of current flowing through it. That is the ideal voltage source. The symbol for ideal voltage source is like this. This is the symbol for ideal voltage source. Okay, this is the voltage is VT and terminal voltage will also be VT as it is the ideal one, and current flowing through this is say I T, and the VI characteristics of this ideal volts would be, say this is the curve is the current, and in this case in this vertical direction is the voltage. So voltage is constant over any value of current, so this is the characteristic VI characteristics of ideal voltage source. But in actual practice, this is not the case. That means this voltage VT is not remain constant at this terminal whenever current flown through it. So here comes another, it's real or practical voltage source. In practical voltage source, this voltage keeps falling as the current flowing through this is increasing, and this terminal voltage is less than the actual generated source battery voltage or source voltage, whatever we call. So in practical voltage cases, voltage of this terminal keeps falling as this current is increasing. This whole behavior we can represent by putting a resistance in series with the voltage source, like this. Say we will draw the voltage practical voltage source like this. So this is the voltage source, and in series with this we put a resistance. Earlier like this, these are our Vt, and current flowing through it is It, and this is our terminal voltage. This is no longer is the Vt. This is somewhat less than this, because some voltage is dropped due to this current, and in this case the Vi characteristics would be like this. This is your current, your voltage. If resistance were not involved, then this is the ideal one, and for practical case it would be this, like this. This is the practical value of voltage across for practical value of voltage characteristic for practical voltage source or real voltage source. Now is the for ideal voltage source, next we will consider ideal current source. Ideal current source. In similar case of ideal voltage source, in this case also, in this case, that means for ideal current source, a specific value of current is always remains constant. That is, if the voltage varies, the current remains always same for at the terminal. Say this is the symbol of ideal current source, and this current, say suppose I, and at this terminal this value of current remains same irrespective of this voltage. Whatever may be the voltage value, the current is completely independent. That is why it is ideal current source. And in this case also, the voltage current relationship will be like this. This is the straight line, this value of the current I. This is our ideal current source. So ideal source, in case of ideal current source, this current value remains constant. Now this is not actually true. In practical cases, we have seen, we may see in our in circuit solution solving problem, we may see that current remain constant always. So in this case also we will discuss, or we will next come to is practical current source. In practical current source, the current decreases as the voltage across it increases. This voltage, whenever this voltage increases, this current also decreases. This likewise, like the practical voltage source, in practical current source we also the circuit we can represent by putting a resistance in parallel with the current source. That means the circuit for practical current source would be like this. This is our current symbol for ideal voltage, ideal current source, and put a resistance in parallel to it. So this is the voltage, terminal voltage, and our current, this is our current I, and the value of this current is different, that is say I1. So this current is reduced, but that is decreasing as the voltage, this Vt value increasing. So this is the practical current source. Likewise, the characteristics in case of voltage, ideal practical voltage, we have seen that the voltage characteristics is decreasing nature. In this case also, for ideal practical voltage source also, practical current source also, say this is the practical current, the voltage current I, this is the voltage, and this is the constant value of current for ideal case. And for practical case, it would not be like this, it will be like this. It will be, this is the curve actually. So this is actually, we can draw this again. Say this is current I, this is the current, this current value, this is I1. So this is not I, this is I1. This is our independent value, real value or ideal value of current, and this is the practical value of currents, and this is our V. Next we will, so this is the ideal current source and this is the practical current source. Now we will discuss about dependent or control source. Dependent or controlled source. In this case, the dependent source or control source is controls, that is if the sources, these control source or dependent source generate a particular value of voltage or current in other particular location in its circuit. Later we will see that when we will discuss about different, we will take out different solution and different problem, and we will try to solve. Then that we will discuss the voltage and current control source. Then we will decide how the voltage and current source control. The actual symbol for ideal voltage or ideal current source is like this. This is the symbol. This is the voltage ideal. This is the practical control. This is the dependent or control source, voltage source. This is the voltage source. Dependent voltage source. And this is the ideal dependent current source. This is the symbol of dependent current source. There are now four possible types of control sources are there. 4 types of control sources, dependent sources. 4 types of dependent source. First is voltage control voltage source. Voltage control voltage source. Then current control voltage source. Then it is voltage control current source. And lastly, current control current source. These are the four types of dependent sources are there. Next we will discuss about our last part in this lecture, which is mesh or loop analysis and nodal analysis. Before discussing this loop and voltage loop or nodal analysis, we will discuss about some terms associated with this analysis. First term is the network. First, what is a network? Network. A network is any possible interconnection of circuit elements or branches is the network. So network is the, say this is a network, this here you can see this is also a network. Any possible interconnection of circuit elements is known as a network. Any possible interconnection. Whereas a circuit, what is a circuit? Circuit is a closed path. Closed path is any circuit is a closed path of any possible connection of interconnection of circuit elements. So circuit and network, what is basically the difference is, network, all possible connection is a network, but not in the case of circuit. Say suppose this circuit is a closed interconnection path. Say this is a T network. Say like this. This is a network but not a circuit, because in this case no closed path exists. So this is a network but not circuit. So all circuits are network, but all networks are not necessarily be circuits. Now in this network there are branches, there are loops, there are nodes. So what are they? This is a branch. This branch is basically a single element. Single element is a branch. That may be a resistance, that may be a voltage source. Okay, this is a branch. And what is the node? Node here, B is a node. Node is any connection between two or more branches. Say this is our one branch, this is another branch, and this is also another branch. So all these three branches meet at point B. So this is our node. So node is basically the connection between two or more branches is a node. For this case, this is also a node. But A and D, these are not a node, because this branch and this branch is basically the same branch. actually same branch. Also in this case also these are the same branch. So these are A and D are not node. These B and C are node. Now come next we'll loop or mesh. What is loop? A loop is a set of branches forming a closed path. Say see, in this case this branch and form a node, form a loop. So this is a loop. Loop means, so see, this A, B, F and A form a loop. So what are the loop? Loop the A, B, F, A. This is one loop. And this loop, so B, C, E, F, B. So B, C, E, F, B. This is also a loop. This, and this is also a loop. C, D, E, C. This is also a loop. Another loop you may consider, this is a super loop or super mesh. We will later discuss about it. This is a super loop. Which is, what is that super loop or super mesh? A, B, C, D, E, F, A. That means A, B, C, D, E, F, A. This is a super loop or mesh. We will discuss later when we will discuss about different problem. So these are the basic terms we need to know before discussing our next loop and nodal analysis. So this is our basically the circuit and their branch, node and loop, all details. Now we will discuss Kirchhoff's law. Kirchhoff's law. Kirchhoff's law. We already discuss about Ohm's law. Now we are going to discuss about Kirchhoff's law. Now see, these two laws, that means the Ohm's law and the Kirchhoff's law, are the basic building block or basic tools of circuit of a current analysis. In current analysis, these two laws are the basic tools for solving problem. Now, what are the Kirchhoff's law? Kirchhoff's law are two types of law. One is KCL. Kirchhoff's current law. Another is KVL. Kirchhoff's voltage law. First we will discuss about Kirchhoff's KCL, that means Kirchhoff's current law. Now what is the Kirchhoff's current law? Kirchhoff's current law is the algebraic sum of currents entering or leaving a node is zero. Is the KCL law. Algebraic sum of currents entering or leaving any node is zero. In mathematical term, write it down. Algebraic sum of currents entering or leaving a node is zero. In mathematical form, summation of current I is equal to 0. Now put a n here. N is equal to 1 to n. This is the n. So this is the notation, mathematical expression of KCL law, where that n n is equal to number of branches or branches to particular node, and any node there may be different branches connected. In this case, see, this is the node 1 2 branches are connected. Likewise, this n is equal to number of branches to the node, and this current in, this is current in, is the nth current entering a node. Entering a node may be entering a node which is positive, assume, or leaving the node. This leaving we regard as negative. Now this just told that the entering nth current entering a node is regarded as positive or leaving as negative. You may consider it is negative, it is positive. Say these are vice versa actually. So let for an example, say we have a network junction like this. Say network junction, say like this, and these are the all branches connected through this network junction. Say this current is entering, which is on I1, and for this also this current I2 entering, and this current is I3 which is leaving, and also this current I4 leaving, and this current I5 is leaving through this junction. Now just told that the KCL law state that algebraic sum of current entering or leaving any node is 0. Now we may say that the sum of current entering through a junction or system is equal to the sum of the current leaving through the network or system. Sum of current entering is equal to sum of current leaving. So in this case these two branches current are entering through this junction, and these I3, I4, I5 are leaving. So according to the KCL law, that current I1 plus I2 will be equal to current leaving, that is I3 plus I4 plus I5. These two currents are entering through this junction, these three current are leaving the junction. Now this natural sign convention, this is important. Sign convention of current. Now say if we consider current entering through a junction is positive, then these two are the current leaving will be considered negative. You may consider vice versa also. That means current entering is negative and current leaving is positive. But in always it is general convention that current entering through a junction or node or any system is considered as positive symbol, and current leaving is considered as negative symbol. So here These already I have written here. You can write is like this. In terms of symbol, current I1 is positive, current I3 is equal, I2 is positive, and these three currents are leaving, so they are negative according to sign convention. So I3 plus minus I4 minus I4 minus I5 is equal to 0 according to sign convention. Current entering we consider positive, current leaving we consider negative. Now, so this is the algebraic sum of current is equal to 0 according to KCL law, and you just simply write it as I1 plus I2 is equal to I3 plus I4 plus I5. What is this equation? These two are what? These two currents are entering through the junction, entering current. So sum of current, these are sum of current incoming or entering is equal to sum of current leaving. So this is the KCL law all about. Next we will discuss another law, that is Kirchhoff's voltage law, KVL. Now Kirchhoff's voltage law states that the algebraic sum of voltages around any closed path or loop is 0. This KVL, Kirchhoff voltage law, said that the algebraic sum of voltages around any closed path or loop is 0. Once again, in terms of mathematical expression, we can write, say, summation of B is equal to 0 and n is equal to 1, and this is capital N and this is our n. Once again, as before, that n is equal to number of voltages in the loop, and that Vn is equal to nth voltage. We generally traverse in a loop in clockwise direction. We generally traverse a loop in a clockwise direction. From a starting point, which may be a node of an element, while traversing in clockwise direction, if we encounter a negative sign, we will write as negative, and if we encounter a positive sign, we will write a positive symbol. Say for example, just consider any a circuit. Say this is the voltage source, and say resistance is connected, and another voltage source, say here another resistance here, and this is a plus symbol, minus, this is the minus and this is plus, and this is our resistance R1, this is our resistance R2, and this voltage source, say this is E1 and this one is E2. Okay, and say the loop, this is a loop, so say consider through this loop we will traverse, as I said earlier, that we will traverse in the clockwise direction, and current flowing through this loop is say I, and the voltage across these resistances say V1, and this voltage across these resistances V2. Now we just told that while traversing through a loop, if we encounter a negative symbol, we will write it as negative. If we encounter a positive symbol, we write it as a positive. And this is the voltage, this symbol across the resistance, this is plus, and also this is a plus and a minus. Now according to KVL law, we write according to KVL, see, we will start from say point here, say this is our A point and this is our B point, this is our C and D. Now start from, you can start from here. Now we will just consider, for example, here we will start from this A point A. Now see, while traversing, see we encounter a negative symbol here, so we write out the negative voltage. What is the voltage? V1. So write minus V1. Okay, now come clockwise direction. Come, while leaving we will encounter positive symbol, so write E2. Then come again, this is a negative symbol, so write the voltage of the resistance across B2 as negative B2, and again we are going, and this is positive, so write as E1. This is the algebraic, this is the total voltage across this loop, and according to KVL, the algebraic sum around any voltages around any closed loop is 0. So this is our algebraic sum of voltage, which is E1 E2 is equal to V1 plus V2. While solving the different kinds of problem, these techniques will be required. So you just have to understand very clearly the sign convention. If you just forgot, what I will discuss is this technique once again. Say, we'll just KVL law is very important for writing voltage equation. Say here with the natural sign we consider assumes sign convention is that while traversing through a loop, we consider if we appear a negative symbol, we will write it down as a negative, and if we encounter a positive symbol, we write it as a positive. So from a point A, we just traversing, we are encountering a negative symbol, so where we have written V1 as negative. The V1 is the voltage across this resistance, and again we are going and traversing through the battery part, and we are encountering positive here, so we written out here positive E1 E2. Likewise the voltage, this is negative and this is positive, So this is the actually the sign convention and writing process of KVL law. So that was all about the KCL and KVL law. Now, before starting the discussion regarding nodal and loop analysis, we will try to know some key points or some rules for solving the problem nodal and loop analyzing problem. Some key points we will try to understand and remember. So our first point is voltage. Say some point, key points, some key points to remember. First is voltage division rule. Voltage division rule. Say two resistances, say this is R1, R2. These two resistances are connected in series and a voltage source is connected in between them. This is the voltage, plus minus, and current flowing through this I. So this is positive, this is negative sign symbol, and the voltage across this resistance R1, say V1, and voltage across this R2 is say V2. So voltage division, just remember that the voltage across this R1 V1 will be equal to that total voltage V into the resistance value, which is R1, divided by sum of two resistances. Okay, so voltage across the resistance is equal to total voltage into resistance of that particular branch divided by the sum of the two resistances. Here it may be 3, 4 or 5 resistances connected in series. Accordingly, in the denominator part, that summation of resistance will be there. Now for this V2 will be, you can say, already you may say that what is this, the voltage multiplied by the resistance R2 divided by sum of this resistance. This is our voltage division rule. Say this is 10 volt, okay, and this V1 say 4 volt, and this V2 is 6 volt. Okay, so what will be the voltage? Sorry, we need to know the voltage V1 here. And so say this value of resistance is say 5 ampere, 5 ohm, and this R2 is say 10 ohm. So then what is the voltage V1 will be? So V1 will be, put it here, 10 into what is the value of R? 5, divided by what is the sum of these two resistance? 5 plus 10 is equal to 10 into 5 divided by 50. For the what is the voltage across this resistance, which is V2 is equal to, put the second equation, this 10 into 10 by 15. So like this you have to apply this voltage division rule for solving the problem. So you have to remember this voltage division rule. Next we will try to understand current division rule. Current division rule. As before, just we consider a parallel resistance R1 is R2 and a voltage source B here, okay, and total current is say I. In this branch current is I1, in this branch I2, okay. And the rule is, this current division rule is, the current across this resistance I, R1, will be I1 is equal to total current into the other resistance, that is R2 divided by R1, sum of these two. Do not confuse with the voltage division rule. We have seen in case of voltage division rule, the total voltage, the voltage across any resistance is equal to total voltage into resistance, the particular resistance across the voltage divided by the sum of these two resistance. But for current division rule, the current across any resistance is equal to total current into the other value of current divided by the sum of the two resistance. So for the current through R2 is equal to I into current voltage resistance R1 divided by R1 plus R2. This is our current division formula. Now say this R2 and R1, there may be different case here. If R1 is equal to R2, what will then? R1 is equal to R2. Then this is equal to this value and this value are equal. So what is the in this case? This current will divide equally between these two resistance. Okay. Now another case, say R1 is greater than R2. Then what will happen? R1 greater than R2 means this R2 is smaller value of resistance. So this R2 will share greater value of current. Alternatively, if R2 is greater than R1, that is R2 is greater than R1, then R1 will be lesser value. So greater amount of current will be shared by R1. Likewise, say says this is our current I, say 20 ampere, and the resistance value, say here it is 10, it is 25. So let's see what value of current I1 and I2. I1 is equal to total current 20 multiplied by, we are going to find the value of value of current I1 through R1. So we have to take the value of resistance R2, so which is 25 according to this current division rule, divided by sum of these two current, which is 25 plus 10 is 35. And for I2, total current it is 20 into the value of resistance I, 10 divided by 35. See from these two I1 and I2 value, 20 into 25, 20 into 10. So this is the I1 is value is I1 value of I1 is greater than I2. That means the lesser the value of resistance, greater the value of current sharing. Just I have told. Okay, so these are the two division rules, current division rule and voltage division rule. Next, our next key points is transformation, delta to star or star to delta conversion, delta to star or Y conversion and Y to delta conversion. Now say this is our delta network. Okay, and the value of resistance, say this is our resistance value Ra, this is resistance Rb, and this is Rc. Okay, and our star value okay. So these resistance values say R3, this is R2 and this is R1. Now first write the relation from delta to star conversion formula. Delta to star, that means originally the circuit is in the form of delta. We have to transform it into a Y connection, Y formation. So last Y formation means we have to find the value of R1, R2 and R3. These three delta connection value will be given. So what is the value of R1, R2 and R3? Let's try to find R1. R1 is equal to, see this R1 is the interconnection value of this R1 is interconnection between these two resistances Rb and Rc. So multiply that resistance Rb Rc divided by sum of all three resistance, that is Ra plus Rb plus Rc. It is quite easy to understand, easy to remember actually. So we are going to find the value of R1. So multiply these two adjacent resistance and divided by whole resistance. Likewise, say for we are going to find R2. So R2, you say what will be R2? The R2 will be the multiplication of these two adjacent value of these resistances, which will be say Rc Ra divided by sum Ra plus Rb plus Rc. Okay, and likewise for R3, these two multiplication of these two will be in the top position. So R3 is equal to Ra Rb divided by Ra plus Rb plus Rc. So this is our delta to star or Y conversion formula. Okay, now let's try to understand the opposite one. That means say star to delta conversion. That is, star network will be given to you. That is, the value of star quantities, that is R1, R2, R3 will be known, and delta value we have to be calculated. And in this network, what are the delta value? That is RA, RB and RC. And what are star value? R1, R2, R3. In this case, R2, R1 and R3 are given. That is known to you. You have to find the delta value. That is RA, RB and RC. So first try to find out RA. Now see, RA, we are going to find RA. Now you look from here, front of RA. What you are seeing? You are seeing these two adjacent, R3 and R2. So you just write it down, sum of these two, R2 plus R3. Then plus you multiply the adjacent two resistance, that is R2 into R3, R3, okay, and divided by this backward resistance R1. Understand the method? Let's start again. We are going to find this value RA. So from look at the forward direction. These R2 and R3 and R2 are the here adjacent value. So write sum of these two, that means R2 plus R3. Then multiply these two divided by R1. This is the transformation. Likewise, you can write say RB. What will be the RB? In front of RB, you see these two are adjacent. Which one? R1 and R3. So write summation of R1 plus R3. Then product of these two, that means R1 plus R3. Then divided by the backward, the last one, the R3, R2. And for RC, the similar case, this is the RC. You look from this side. These are two are your adjacent side. So write sum of these two plus product of these two divided by the last one, R3. So this is the basic formula. Actually, in this case you need not to remember this formula. You have to remember the techniques. What techniques is applied to find out the delta to star and star to delta conversion. In the delta to star conversion, I just told that you have to multiply the adjacent value of the resistance divided by sum. And likewise for Y to star conversion, you have to look forward and write the sum of the adjacent value, then also sum of the product of work divided by the third one. Okay, this is the technique applied for finding the value of star or delta conversion resistances or element value. Our next key points we have to remember is source transformation. Source transformation. Source transformation, actually say we have a voltage source. We need to transform it into current source or vice versa. What will be the technique applied for this? Say suppose we have a voltage source here. and in series with the resistance R, and this is our voltage V. Now you need to transfer, or we have to transform this current source into, this voltage source into current source. What you have to do is you simply replace that voltage source into a current source and that resistance in parallel, like this. Put that voltage source as current source and put the resistance in parallel the current source. And what will be this current value source, the source of the current value, and what will be the resistance? Resistance value will be remain same, that means the R, and that current value will be the voltage divided by the resistance value. That means this current will be V by R, and this is vice versa, actually vice versa. Okay, voltage source in series with the resistor can be transformed into a current source in parallel with the resistance. The value of the current source will be the voltage source divided by the in series resistance. This is the basic transformation technique.